Hello everyone, and welcome to this presentation about how to parameterize and optimize over states at the boundary of the tensor network variety. This is joint work with Daniel Stilck França, who's also in Copenhagen, Fulvio Gesmundo, who's now at Leipzig, and Matthias Christandl, who's also in Copenhagen. So this is the plan for the next 30 minutes. I start out with some background in tensor networks, which will lead to the idea of boundary states, and then show you how to construct an ansatz class that captures these boundary states. And finally, I discuss how to optimize within this class and show you some numerical results. But let's start with the tensor network part. One problem we face with quantum many-body systems is that the underlying Hilbert space dimension explodes exponentially with the number of subsystems. And we can interpret this somehow as an over-ambitiousness on our part, that the Hilbert space will describe any physical possible state of the system, whereas oftentimes we have additional assumptions and would be more interested in the physically reasonable. And that there's a difference between these two concepts you can already see if you look at the entanglement entropy. Namely, if we pick a random state in the Hilbert space, then the entanglement entropy will satisfy a volume law. So it will scale with a number of the subsystems within our subset A, whereas physically irrelevant states like ground states of local gapped Hamiltonians in one dimension will satisfy an area law, where in one dimension the entanglement entropy stays constant even if we increase the system size. So our idea is now to somehow single out this physical corner of Hilbert space, find an efficient parameterization of the states that are contained in it, which have already this built-in area law. An example of a class of states that satisfy this are matrix product states. So this is a class of states that arises in the following way. We take maximally entangled states of some fixed dimension D, and we place them in our one-dimensional system such that each maximally entangled state is shared between neighboring lattice sites in our one-dimensional lattice here. And then in order to get the physical state out of the system, we apply local linear maps to this joint space of the two adjacent maximally entangled states shared with the two neighboring sites. And this will map our system from this joint space C capital D tensor C to the capital D into the physical space C to the small cap d here. And what we get out then is the state of this form. So we have our states phi, which arises from applying this local linear maps, A nu, to this underlying network of maximally entangled states. So this here we would call a matrix product representation of the state phi with bond dimension D corresponding to the dimension of the maximally entangled state. And if you make a quick parameter count, then we see that this number scales linearly in the system size by just specifying the local linear maps A at each of the lattice sites. And this procedure can now easily be generalized to higher dimensions and more complicated situations. So given any graph, we associate to each edge in this graph a maximally entangled state, similar as before in the one-dimensional setup. And then in the next step, we apply again local linear maps to the joint local space of all the incidenting maximally entangled states that we have at one lattice site or at one vertex of the graph. And then exactly in the same manner as before, we get a state phi out here of this form where we have this underlying resource state, this network of maximally entangled states parameterized by this graph, and we apply these local linear maps to it in order to get the physical state out. And that is what we call a tensor network representation of fixed bond dimension D, where the bond dimension D again corresponds to the dimension of the maximally entangled state. And then a natural question to ask is, what's the expressive power of such a tensor network? Namely, for a fixed graph and given state phi, we can ask what's the minimal bond dimension that we need in order to represent the state with respect to this tensor network, and that's what we call the bond dimension of phi with respect to G. And we can also formulate the question the other way around. We can fix a bond dimension D and then look at the set of all states that have an exact tensor network representation with respect to the underlying network of maximally entangled states and see how big or large the set is, which kind of states it contains. And then we can enforce additional constraints, for example, translation invariance, where we require that the local map that we apply is the same everywhere. So we're only allowed to choose a single map, and this has to be rolled out on the whole graph. And then we would be interested in the structure of this set TNSG for fixed bond dimension. So what kind of states are contained in there? And one result by Landsberg and co-workers is that if the graph that we fix has cycles, then the set is not closed. And we are interested here in the question, what kind of states are on the boundary, and can we use this to parameterize the states that we can encounter there? And this brings us to the second part of the talk. And the first idea I want to introduce for these boundary states is that of the border bond dimension. So we've seen the bond dimension a second ago. It's a minimum D that we need in order to find an exact representation for our state in this set of all tensor networks with fixed bond dimension D. But now, if this set TNS is not closed, we can alternatively ask to find a representation of phi in the closure of the set. And that's the border bond dimension. So the definition is very similar to that of the bond dimension, but here we do look for phi in the closure of this set TNSGD. This idea of a border bond dimension is very reminiscent of the idea of rank and border rank in the theory of tensors or algebraic complexity theory, where instead of applying local maps to an underlying network of maximally entangled states, we would apply those maps to an underlying GHZ state. And this problem has been well studied in algebraic complexity theory. And here we look at this in the context of tensor network states. Now, we can, of course, also restrict again to the translation invariance setting, where we require to apply the same map everywhere and ask the same question about bond and border bond dimension. And since we optimize over a larger set in case of the border bond dimension, this will always be smaller than the bond dimension. But at the end of the day, we want to know how large a separation can we prove and which kind of states will achieve such a separation. A helpful concept to address this question will be that of degeneration, which is a generalization of our local linear maps that we have already encountered. And that's what I'm going to introduce now. So if we look at the closure of this TNS set for fixed bond dimension, and we take a state in there, of course, we will find a sequence of states approximating the state phi, either because phi is already in the interior itself, or if it's in the boundary, we can find an arbitrary good approximation. Now, it turns out, if we look at the algebraic geometry of these sets, then we can see that we can choose this approximating path from, let's say, here to the boundary, always as along a rational curve, if phi is in the closure of the set TNS. And this means that we can realize the state in the boundary with the help of local linear maps, but with a twist, because now these local linear maps depend on a parameter epsilon polynomially. So each local linear map I can expand in this parameter epsilon. And then if I apply these maps to my underlying network of maximally entangled states, I will get the state phi in the boundary that I'm interested in lowest order in epsilon. But then there are some additional terms that I have to consider. And such a representation of phi as a lowest order in such a polynomial expansion is what we call a degeneration. It has an approximation degree, that's the order, the lowest order in epsilon we have here, and an error degree, that's the number of terms that, the number of error terms that appear. And then if you have such a degeneration, it's easy to construct an approximating sequence. We just divide by epsilon to the minus a and send epsilon to 0. And then the expression here will clearly converge to the state phi. But what is important to note is that this limit only will happen on a global scale. So we do get out the state phi globally on the system, but we do not get a limit for each of these maps, these local maps here individually. So if we there just set an epsilon to 0, we will not get the state phi out in the, and then apply it. We will not get the state phi out, but we have to apply this polynomially depending maps to our state and then take the limit of epsilon to 0 in order to realize the state at the boundary. And the second thing I want you to note is that along this path, so for each fixed epsilon, we still have a bond dimension D representation of our state because we move inside of the set T and S. So for fixed epsilon, the bond dimension is still D. And the question is whether the state at the boundary can have a larger bond dimension than the states in the interior. And such a difference would then exactly give us a separation between the bond and the border bond dimension. And it turns out that this is indeed possible. And here come some examples. The first example that I want to present to you is the W state with periodic boundary conditions. So the graph that we consider is the cyclic graph with L vertices. And then for the W state in the translation invariant setting, where we enforce the same map on all lattice sides, we can show that the border bond dimension in the setting is equal to 2. So independent of the system size, whereas we get a lower bound on the bond dimension in the translation invariant case for the W state, which grows with the system size. And this lower bound is derived by some recent results on the quantum Wieland inequality. So by making the system size larger and larger, we can get a separation here, which is arbitrarily large between the border bond dimension and the bond dimension. But note that for this particular example, we have to insist on translation invariance and periodic boundary conditions, because if we don't, in the open chain case, the graph does not have a cycle, so the tensor network set TNS in that case would be closed and we would not have a boundary to consider in the first place. So the separation here arises for this particular example of the W state really in the translation invariant setting. So you can ask whether the W state is the only example that we have, but we can actually derive a whole family on the cycle of states for which we find such a separation, namely we call those weight states. So we sum computational basis states such that the sum of the basis labels is equal to some fixed weight A, and this fractura D is the local dimension of these states. And for these states, we also find that the border bond dimension is upper bounded independent of the system size, namely exactly by the weight A plus 1, whereas for the bond dimension, we get the same lower bound as for the W state, again, by using the quantum Wieland inequality. Now, what happens beyond the cyclic graph and translation invariance? So if we just drop translation invariance, we see that the separations that we can get in this general periodic boundary conditions case are bounded by the square of the bond dimension, because then the closure one can show is contained in TNS for the cycle D squared, because what we can do is we can cut the circle open and like rewrote the last maximally entangled state through the entire chain. And for more general graphs, we get an inclusion that the bond dimension scales as D to the number of edges minus the number of vertices plus 2. So also there we can, like for a given graph, get an idea what kind of separations are possible at the end of the day. Okay, so after these more abstract examples, let me make the connection back to quantum many-body physics and show you an example where a boundary state arises as the ground state of a local Hamiltonian. So we're still in the translation invariant setting with periodic boundary conditions in one dimension. And for odd L, we can define this local Hamiltonian here. The details are not important. The only thing that you should notice is that this is a nearest neighbor interaction that we specify plus an on-site term. So this is a normal local Hamiltonian. And as it turns out, this Hamiltonian has a unique translation invariant ground state in its ground state subspace. And for this particular state, we can again show a system size dependent separation between the bond and border bond dimension 2 versus the already known 1 to the L to the 1 over 3 relation from before. So also in this more physical setting, these states actually arise as ground states of local Hamiltonians. And this exactly brings me to the next part of the talk, where I want to present to you how we can build an ansatz class that contains these boundary states. But the problem that we face is that these boundary states, we can only represent them approximately in terms of these degenerations. But what we would like to get would be an exact representation of these states. And then we can use tools from algebraic complexity theory to derive such a representation in the following way. So what we can show is that if you have a state in the closure of the set of tensor network states with a fixed bond dimension, and it is given in terms of a degeneration, which has an approximation degree A and an error degree E, then if we supplement our network of maximally entangled state by a weight state, which has the parameter A, so the weight, which corresponds to the approximation degree, and a local dimension, which is at least as large as the error degree of the degeneration, then we can write this state as the application of local linear maps BV to this network of maximally entangled states, tensor this additional resource state, this weight state. So now we have again an exact representation in terms of these local linear maps, but with a slightly changed resource states on the right-hand side. And down here is a little cartoon of this. So at the beginning, the maps still depend, the maps that we apply locally still depend on this parameter epsilon polynomially. But if we put in also this chi state, then we get an expansion of the state phi that we are interested in and where the epsilon has disappeared. And in the background, what we do is we recognize that phi of epsilon is a polynomial in the epsilons. And what we would like to do is we would like to divide by epsilon to the A and send epsilon to 0. But we cannot evaluate this function directly at epsilon equals 0. But what we instead can do is we can interpolate this polynomial to 0 if we evaluate this function phi f epsilon divided by epsilon to the A at sufficiently many fixed epsilons. And then we can implement this interpolation in terms of these local maps here if we supply this additional weight state to the whole mix. And in this way, we get an exact representation of our state. And now we have everything in place to write down our new ansatz class for these boundary states. So what we do is we supplement our network of maximally entangled states that comes from the graph by weight states in order to get these boundary tensor network states, the BTNS set. And this is a set for fixed bond dimension, fixed approximation degree, maximal error degree, frag delta, and physical dimension D. This is a set of all phi that we can construct by applying local linear maps BV onto the network of maximally entangled states, tensor the corresponding weight state chi. And as we have seen in the previous slide, this set BTNS now actually contains states from the boundary of the tensor network variety, namely if the underlying degeneration with its parameters satisfies the conditions that we just discussed. You should note that this set does not only contain the states in the boundary, because we do not insist that these local maps here arise from a degeneration in the original formulation, but we allow for arbitrary linear maps here, but we contain the boundary states. You could think about this as a relaxation of this condition on the local BVs, because if we would insist that they should arise from a degeneration, we would have to check like system size many non-local constraints equation. And basically we drop this part, which enlarges the set of states that we can represent a bit, and at the same time makes optimization over the set efficient, which we will see in a second. But before that, I would like to discuss one subtle point, namely whether we even need this kind of ansatz class in the first place. Because what I told you is that we look at states at the boundary, so there is this degeneration, and we naturally get an approximation of our state phi if we like put in an epsilon, which is small enough, and then look at the states epsilon to the minus a, phi of epsilon. Right, and then tensor networks are an approximation of our physical states anyway. So if we think about the theorems that we know, then they only promise us that the ground state of a gapped Hamiltonian in one dimension will be arbitrarily well approximated by a tensor network state where the bond dimension scales efficiently in the error that we make. So why shouldn't we do the same here? So we just use this expression here as an approximation of our state phi that we're interested in, and then do our normal optimizations to find a state which is, well, not phi exactly, but very close to the boundary. And in principle, that would be possible, but it leads to numerical problems that I would like to briefly elaborate on. Namely, let's assume that we want to approximate an extensive observable like the energy for a local Hamiltonian on the state, then typically what we need in order to get an additive error of the order of delta, you would have to approximate the state phi on the order of delta divided by alpha, L to the alpha for some alpha here. But if we want to achieve such an accuracy in our approximation, we have to choose the epsilon in this expression here also at the order of delta over L to the alpha, which in turn means that the norm of this degeneration will also be of the order delta over alpha divided by delta to the a, so this is the approximation degree, divided by L to the alpha times a here. So now if you think that you want to compute an expectation value, we have to divide by this norm. So we divide by a quantity of this order and multiply it with a quantity in the inverse order. So we need to have a polynomial precision in all the parameters L to the alpha and delta to the a at the end of the day. And this leads to numerical instabilities, and these can actually be observed. So here's an example of a gradient descent where we try to find a state in C9, tensor C9 and tensor C9. So the actual structure of the state is not so important. The important part is that we know that the border bond dimension is smaller than the bond dimension. And then we try to find the state once with a normal tensor network approximation and within our new border tensor network state class. And so for bond dimension equal to 3 and bond dimension equal to 4, what you see is something very typically happens. So we have an initial decrease in the distance of the state to the state that we are looking for, but then this convergence basically drops to 0. So there's not much change anymore. I mean, here the green line is very slowly still converging, but it really takes forever. And this is really what happens if you run into one of these degenerations where we try to follow such a degeneration to the boundary of the tensor network manifold here. Whereas if we directly optimize within our adapted class, which is the blue curve here, then already a bond dimension 3 plus an approximation degree 1 is sufficient to very quickly reduce the distance to the desired state that we are looking for. And then you can see that if you make the bond dimension large enough, that the state is actually again contained in the tensor network set that for fixed bond dimension, then we can also recover the state with the normal approach. But it should be noted that the blue curve here has fewer parameters than the red curve that we have to fit. So this is easier, and this is why it makes sense to consider this extended class, even though these states can be approximated arbitrarily well within the set TNS. And since I talked now already about the gradient descent method, I would now like to come to the actual optimization algorithm for this ansatz class. And the first component in this endeavor is to find a way to efficiently compute expectation value in this boundary tensor network class. So remember, this class is given by the states which can be obtained from applying local linear maps to our network of maximally entangled state, tensor the weight states chi here. And then we can basically describe two strategies in order to compute expectation values. One strategy uses that we can express these chi states as matrix product states of constant bond dimension, A+1. And then we can basically, for example, for a lattice, just add this additional MPS in the background of the state and do a standard contraction scheme in order to compute the expectation value. So by this, if we talk about lattices and simple graphs, we can show that the boundary tensor network states can be embedded into a tensor network where we have a blow up of the dimension by this factor A+1 because we snake this MPS through the bond dimension that's already there. And then we pay this poly overhead in the contraction, but otherwise everything is unchanged and we can just use the standard methods. So if the separation for these boundary tensor networks is large enough, this is still a price worth paying in order to actually get these states at the boundary within our ansatz class, also in a like numerically stable manner. And the second strategy is what we call the border rank strategy, where we use that we can express the weight states as degeneration themselves, their border rank as a tensor is A+1. And then similarly, as we turned degenerations into exact representations of the state via interpolation to 0, we can do the same thing for the expectation value in terms of epsilon. Which of the two strategies is better to use is a bit subtle. It depends on the lattice and the properties of the graph that we're considering. But in the following, all numerics that I present use the matrix product strategy. And then we would like to use this ansatz class in order to find ground states and ground state energies of local Hamiltonians. And it turns out that both the gradient descent and imaginary time evolution can be reformulated in terms of this boundary tensor network ansatz class. I'm not going to go into the details here, but it only requires minimal changes to the existing algorithms that are out there. So as a final part of this presentation, I would like to present to you some numerical results with this algorithm. The first one is for gradient descent. And here we take the example of the Hamiltonian from the beginning, where we can observe in the translation invariant ground state of the system, system size dependent separation between bond and border bond dimension. And indeed, this is also what we see if we use gradient descent in order to try to minimize the ground state energy. Here, so the blue line is our new ansatz class for bond dimension 2 and approximation degree 1. So we see a nice convergence here to 0. Whereas for the normal bond dimension, where we do not explicitly include states at the boundary, the convergence is much less favorable. Instead, we see this typical behavior that happens if you try to find a degeneration, that initially there happens nothing, then there's like a jump to some finite value, and then you end up in this very slow regime that you continue for a long while. And the second example that I would like to show you, which is maybe a bit more physical, is an imaginary time evolution for the isotropic Heisenberg chain. And here we compare directly on 12 lattice sites our boundary tensor network with bond dimension 10 and approximation degree 1, though this is a blue curve. Again, we look at the logarithm of the energy that we can achieve, and we compare this with the bond dimension 15 imaginary time evolution. And again, we see that in the setting here, somehow these boundary states do seem to have a nicer convergence behavior than if we just restrict ourselves to a normal tensor network representation. And with that, I come to the end of my presentation and would like to briefly summarize our findings. So starting from tensor networks and the fact that the tensor network manifold for fixed dimension can be an open set, I introduced the idea of bond and border bond dimension. And the question was whether we can find in the boundary of the tensor network manifold states with a large bond dimension that nevertheless have a small border bond dimension, so are more efficiently representable in this kind of border bond dimension description, where we use degenerations in order to parameterize these states at the boundary. And indeed, this was possible. And for example, for these weight states, we could get system size dependent separation between the bond and the border bond dimension. Then we used this insight and the degenerations in order to write down a new ansatz class for boundary tensor network states given by local linear maps applied to the normal network of maximally entangled states, supplemented by these weight states here in order to get exact representations of boundary states. And then in the last part of the talk, I showed you how to optimize in this class and showed you some first numerical results. So where to go from here? So first of all, everything that I told you also conceptually makes sense in higher dimensions, and we are very interested to pursue these directions, in particular because we think that here the savings should be even larger, given the fact that there are much more cycles in a two-dimensional system than in a one-dimensional system. Furthermore, the idea would be to go beyond ground state properties, but instead look for excitations, because like the example of the W state seems like a paradigmatic case where you put a local excitation in your system that you then can describe somehow delocalized as a superposition of shifted local excitations. And on the more abstract level, so we saw that in principle, it could be possible to get quadratic savings on the ring, for example. I would be very interested to find out whether this is actually realizable, or whether we can improve the upper bounds that we have derived now to see that actually the separations that you can get in one dimension should be linear after all. And with that, I thank you for your attention and hope to see you in the question session.